In this video we're going to study the last two countability axioms, and we'll see a theorem that relates these two axioms with the second countability axiom that we saw in our previous video. The third countability axiom doesn't actually have that name. We say that a topological space is Lindelöf if any covering of X contains a countable subcollection covering X. So this definition is a bit similar to a space being compact. It's a bit weaker. Instead of asking for a finite subcollection, we're asking for a countable subcollection. Obviously, if a space is compact, it will be Lindelöf because any finite subcollection is in particular countable, but not every Lindelöf space will be compact. Now let's see the last one. This other definition usually appears on the first analysis courses, but we say that a space is separable if there exists a countable subset of X that is tens in X. And by tens, we say that D is tens in X if the closure of D is equal to X. So if in a space we find a set for which the closure is X and the set is also countable, then we say that the space is separable. An example of this are the rational numbers that are tens in the real numbers. So now let's work on the result that will combine these two axioms with the second countability one. This theorem shows us that any second countable space is both Lindelöf and separable. Let's look at the proof. Given that X is second countable, we know that there will exist a countable basis B of X. To show that the space is Lindelöf, what we have to do is take any covering of X and find a countable covering from that original one. So let's take U alpha, a covering of X. Given that this basis is countable, what we're going to do is take for each element in the basis one of the sets in the covering such that this condition is satisfied. Now let's see that this new family of sets is also a covering of X. For this, let's take X, an element in the space. We will need to find one of these elements that covers it. So, given that B is a basis, we know that there exists B sub n, some element in the basis B, such that X is an element of B sub n. But now we can take in the new sequence such that Bn is a subset of U sub n. But then what we have is that X is an element in Bn, subset of Un. And so this proves that U sub n is a covering of X. But given that this basis was also countable, then this covering is also countable. What we did here is that given any covering of X, we found a subcollection of that covering that is countable and that also covers X. And this proves that X is Lindelöf. Now let's prove the second one. We know that X is a second countable space, and we have to prove that it's separable. Now, for each element in the basis, we will choose an element in the set. This will give us a countable set, Xn. Well, let's call this set D and prove that it's tens in X. But this proof is actually quite trivial, because given any element in the space, we know that there will exist some B sub n in the basis such that X is an element in B sub n. But the intersection of this neighborhood of X with D is some set that contains Xn, because Xn was an element in Bn and is also an element in D. So what this gives us is that X is an element in the closure of D. And because X was just any element in the space, then the closure of D has to be the entire space. Also, D is countable because the basis is countable. And with this we have that our space X is separable, which is exactly what we wanted to prove for the theorem.